name is Amani Smith, and this is my Lab 4 report. So, a quick overview. The purpose of this lab was to observe and measure the distance dependence from the magnetic field of a bar magnet. And we did this by measuring the strength of the magnetic field due to the bar magnet off and on axis. So here's a quick preview of the results. We measured that the magnetic dipole moment was 3.115, and we found N to be negative 3.2154. So the key physics principles used were one, the Biot-Savart law, which gives the relationship between the magnetic field and the velocity due to a charged particle, and then we have the magnetic dipole magnetic field equation, which gives us the magnetic field due to a dipole at a certain location. So for our experimental setup, we first had to align the phone with align our phone's magnetometer with the Earth's magnetic field, and then we had to find a certain distance from the magnet, both on the x and y coordinates, to find the position of the magnetometer within the phone. And then for the experiment, we're going to define the system as being the bar magnet, and everything else is external. We then measured how far the distance in meters the magnetometer was to give certain readings in micro teslas. So first, we repeated this 5 different times with 20 microtesla, 70 microtesla, 120, 170, and 220. We then repeated for each different micro Tesla measurement in the x coordinate. We took 3 different measurements and we averaged this, and then we linearized this using this graph to give this equation right here. We then use our linearization equation from the spreadsheet to find our n and k values. We then found the magnetic dipole moment by setting this equation equal to the dipole approximation to give us 3.115. Now for the off-axis portion of the experiment, we have pretty much the same setup for the on-axis. However, now we have an added y component with d perpendicular on both the x and y lengths, and we found d perpendicular by setting the magnet a certain distance away to give the net magnitude of the magnetic magnitude from the magnet to be 100 microtesla. And then we had to, for the y component, we had to compensate for the Earth's magnetic field, giving us this b net right here, and we repeated this 3 different times to give us an average seen over here. Here for my computational model, we can see I started by creating a function for the electric field or magnetic field for the dipole approximation, and then over here I created 2 arrows on axis representing the magnetic field at a certain distance, and then here we have 4 different off axis or perpendicular arrows representing the magnetic field at those locations, and then we have 1 magnetic field location arrow to represent that at a 45-degree angle. So here we have a visualization of the computational model with the orange representing the on-axis magnetic fields, and then the blue representing the perpendicular magnetic fields, and then we have the pink representing the off-axis magnetic field at a 45-degree angle. And by plugging in our magnetic dipole moment calculated earlier, we can find the B field at this 45-degree angle at a distance d. And we can see here this is very different from our observed B field, and some potential sources of error may include the fact that we assume that there are no external magnetic fields from our computers, maybe from our phones. We assume these to be negligible, and then we also assume that the bar magnet was a dipole. Now for the discussion questions, due to our observations, we found the first and the fourth statement to be true. When the magnetometer was far away, we saw that the actual magnitude within the x direction would decrease close to 0, and then as it moves closer, the measured x component would increase. And this aligns with the Biot-Savart law from our key principles. And for our hypothetical situation, what if we didn't compensate for the Earth's north magnetic field? This would interfere with some of our magnetometer measurements, and this would skew our data by quite a bit. And then what if what if we use two magnets instead of one connected by the poles? Our direction would remain constant because the magnetic dipole moment would stay the same. However, the magnitude of the magnetic field would increase. It would double, matter of fact.